I'm Parker Abercrombie, and I'm a software engineer at NASA's Jet Propulsion Lab. Today I'm going to be talking about how NASA uses the cloud to enable virtual reality Mars. So the project that I'm going to be talking about is called OnSite. And OnSite was developed as a collaboration between JPL and Microsoft, and it allows scientists and engineers to work on Mars through the power of virtual reality. So the way this works is the user puts on a virtual reality headset, and we use the HoloLens device from Microsoft, and then they see Mars around them in their office, and they can walk around and explore the scene as if they were actually there. So the reason that we do this, beyond just that it's fun, is that you can get a different sense of the nature and the scale of the Martian terrain by looking at it in an immersive 3D experience than you can get by looking at a 2D image on your computer screen and then trying to reconstruct the 3D scene in your head. So our users are scientists who work with the Curiosity Mars rover, and they're mostly geologists. And when geologists study a place on Earth, they actually go out in the field and they walk around and look at the rocks. So we're trying to give them as close to that experience as possible for Mars using the technology that we have available today. So to make this experience possible, we needed to create this virtual reality scene of Mars. But the rover moves every day, and we wanted this tool to be useful operationally, so we actually needed to not just do this once, but we needed a way to create these scenes easily and automatically as the rover moves and new imagery is downlinked. So the OnSite team built a custom image processing pipeline that takes stereo images from the Curiosity rover and builds a 3D reconstruction of the terrain around the rover. And then we built a cloud architecture to let us run this automatically in the cloud as soon as new data comes down. So this is a cloud talk today. I'm not going to say much about virtual reality, and I'm not going to get into much detail about image processing, but I'm going to talk about how we've used cloud computing and open source technology to enable us to run this process automatically when new imagery comes down and push that out to our users. So by the end of my talk, I hope you'll have learned a little bit about how we've used the cloud to solve our problems. Hopefully you'll get some ideas that might apply to your own problem domains, and I hope you'll be excited about space exploration. So the data that we work with comes from this instrument, Curiosity. Curiosity is a rover on Mars. She landed in August of 2012, so she's been on Mars for about 3 years now. And to give you a sense of scale, this thing is about the size of a small Jeep, so it's pretty big. Curiosity had a lot of different instruments on board. The ones that we work with primarily are the stereo cameras on the rover mast here. You can actually kind of see the two eyes of the stereo mast cam there. So as the rover drives, it takes these pictures, and it sends back the pictures to Earth, and then we take them and we process them into this. So what we're looking at here is a 3D reconstruction of a scene of Mars along Curiosity's drive. And I want to point out that everything you're seeing here is real. This is all real imagery sent back by the rover. There's no artistic retouching, and this is produced completely automatically with no human in the loop. In the front here, you can actually see a little bit of the rover's shadow that was captured in the imagery because the sun was behind the rover when that picture was taken. If anyone follows the Mars Science Laboratory mission, this mountain coming up in the background is Mount Sharp. This is Curiosity's final destination. And right now, the rover is exploring dark dunes that will be coming into scene just in a second here. Kind of there's this band of dark dunes at the base of Mount Sharp, and that's where the rover is today. So this is where we want to get. We want to take the stereo images and make a scene that looks like this. But before we do that, let's back up a step. So this is Mars as seen from orbit. The Curiosity rover is exploring Gale Crater, which is the yellow dot here. I'll zoom in a little bit. So the blue path here is Curiosity's traverse. So everywhere that you see the blue path is somewhere that the rover has driven or stopped and taken images. So what we're looking at here is Mars as seen from above from an orbiter. And that instrument is the Mars Reconnaissance Orbiter. It has a number of cameras and sensors on board that produce these orbital maps of Mars. And this imagery is at about 1/4 meter per pixel, which is fairly good as orbital imagery goes, but if you're going to put it in virtual reality and stand on it, 1/4 meter pixel is pretty big. So as Curiosity drives, she takes these images, and then we take those and we build these 3D scenes. And we need to do this for basically everywhere along the path. So everywhere the rover stops and takes pictures, we consider a scene, and we'll build a reconstruction of that part of Mars. At some point, we would like to link these all together into one kind of super scene of all of Mars, but we're a little bit a ways from that today. So I'm not going to get in too deep into image processing in this talk, but I'll give you at least the kind of the high-level version of what we do. So we take the stereo images, and using a stereo correlation algorithm, we derive a range from the camera position to each point on the terrain. And from those ranges, we can create a point cloud. And from that point cloud, we can do a surface reconstruction that gives us a mesh geometry for the scene. And then we can take the images from the rover and paint those back on top of the mesh to get the fully textured mesh. And you can kind of see a little bit of that process here, where in the background is kind of hard to see in the projector, but you see only the wireframe mesh geometry of the scene. And then as you get closer in, you can see how the mesh and the texture start to interact until you have the final product appear next to the rover's wheels. So when we're doing this, there's a couple different types of imagery that we need to combine because we don't have high-res color imagery of all of Mars, unfortunately, especially where the places where the rover is just arriving. So the main types of images that we work with are black and white images from the rover's navigation cameras, which give fairly low-resolution grayscale imagery. In color mass cam images. So this is the high resolution science camera. And where we don't have either of these types of imageries, then we'll fall back to orbital imagery from the Mars Reconnaissance Orbiter. So for every part of the mesh, we'll have some type of imagery, and some is better than others. So there's an element of sensor fusion in how to stitch these things together in a way that you're using the best possible data for each part of the mesh. And, sir?
What software are you using to take the stereo images and build a depth?
It's an in-house pipeline. Yeah. So there's an element of sensor fusion in combining these things into a good-looking final product. And for the purposes of my talk today, I'm going to treat that as kind of a magic black box where images come in, magic happens, and then this textured mesh comes out the other end. And then once we have that textured mesh, then we can load it onto the on-site software running on the HoloLens and look at it in virtual reality. So we've been running this pipeline for about a year now. We've processed several hundred scenes all along the rover's drive. The size of the scenes varies quite a bit depending on how much input imagery is available. In a place that the rover has been exploring for a while where we have a lot of images, we might have several thousand. In a place that we just arrived, we may only have a handful of images. A typical scene is about 1,000 images, about 5 gigabytes of data. And over the course of our processing, we'll crunch that into a couple hundred megabytes of mesh, and that process takes a couple hours running on a single node. So when we started this project, we developed this software just on our development workstations, and we would, do kind of the simple thing that you would expect. You would, expect your input files to be in one directory, and you put your output files in a separate directory. And when we went to run it, we'd copy the appropriate input files to directory A, hit go, wait a couple hours, and then grab the results from directory B, and then put them where they actually needed to be. And that worked pretty well for development, but it obviously doesn't scale very well when you move into operations. So that's what led us to port this into the cloud. So at the high level, we have a batch processing problem where data comes in, we need to detect when that data is available, we need to pull it down, run this long resource-intensive task that produces some output. We need to put that output somewhere where our users can get to it. We want to be able to see what's happening as the system is doing all of this, and start new builds and stop builds that are running, see the status of what's currently running. And we have a bursty workload where we get downlink from Mars on a roughly daily basis. So downlink happens, we need to spring into action, grab the new images and build the scene, and then we kind of go back to idle till the next downlink. So we don't want a lot of expensive computing resources running while not doing anything and costing money. So we built a system that we're running in Amazon's Web Service Cloud to solve this problem. And here are some of the Amazon services and open source technologies that we're using in this system. We use the Jenkins continuous integration system both to compile and run our image processing code and tests, but also to actually run the image processing jobs. So we can treat them as if they were compilation jobs. We use Ansible to deploy and configure our Linux servers. We use the loopback Node.js framework to expose a data API on top of our database. And we use AngularJS and Bootstrap to create a dashboard view of the system. And I'll go into a little more detail on how we're using all of these. So here's the high-level schematic view of the system. Things really start on Mars, where the Curiosity sends data down to Earth. It goes into the mission data system, and it's cataloged in that system. And that's where we pick it up. Now, our system falls into kind of three main pieces. We have a build manager whose job is to find out when new data is available, index that data into our database, and request that builds start. We have a build cluster that has a master node and a fleet of worker nodes that actually do the terrain builds. And we have a distribution system, which pushes stores the results and pushes them out to our end users. So first thing happens, data comes down from Mars to Earth. The build manager periodically pulls for new data, and as soon as it finds some, it indexes that data into our database. Then it requests that the build cluster start a new build. The build master, Jenkins, will find a worker to run the build, creating a new one if necessary. That worker pulls the data that it needs to do its job from the mission data system, runs the job, and then pushes the results out to our S3 bucket. Then it notifies the build manager that a new build is completed, and then our users, the next time they launch on-site, will pull down the new data and see the latest location on Mars. So here's how Amazon's web services fall out in our infrastructure. Imagine most people in this audience are probably familiar with these, but I'll very briefly introduce them in case anyone's not. In the middle column here, these are all EC2 instances, so these are all virtual computers running in the cloud. The build manager and Jenkins are kind of medium-sized instances, and these are long-running. They're pretty much always available. The workers are the beefy machines that actually do most of the image processing, and these we treat as disposable resources. We create and destroy those all the time based on our workload. We use the SQS, the simple queue service, to communicate between the build cluster and the build manager, and within the build cluster itself. So we have a couple queues set up for different types of communication. We use the relational database service. This is Amazon's relational database as a service. It's a kind of a veneer over a relational database to store information about available source data and completed terrain builds. We use S3 to store the results of our builds. And CloudFront is Amazon's content distribution network. So CloudFront takes the files that we put into S3 and then pushes them out to data centers that are geographically closer to our end users so that they can experience faster download times. So this being a Linux conference, I'll also talk about operating systems. Our build manager in Jenkins, we run in Ubuntu Linux, and our worker nodes we actually run on Windows. So it's a heterogeneous system where we run both Linux and Windows machines. And to communicate between those machines, Jenkins helps us. Jenkins is pretty good at sending jobs out to the Windows machines. And for other data, our usual solution is to use a simple queue if it's a small amount of data, or to push results up to S3 and then pull them down on the other end, as long as it's not a terrible huge amount of data and it's all within Amazon's data center. It's pretty easy and it works. All right, so I'm going to go through each part of the system in a little more detail, and I'll start with the build manager. So the build manager's job is to discover when new data is available, orchestrate the terrain reconstruction jobs, and present a dashboard view of the system. It also is the kind of the interface between the rest of the system and the database. So it exposes a REST API. We used the loopback as a Node.js framework to build a REST API on top of our database, and the build manager exposes that to the rest of the system. So nothing else in the system needs to know anything about the database. We also have a dashboard view that we built using AngularJS and Bootstrap, and I'll demo that now. So this is our build manager dashboard. So this is created with AngularJS and Bootstrap. At the top, we have some summary statistics about the number of scenes we've built and the number of builds of those scenes. I can see the status of the cluster. At the time I recorded this, there were two nodes running, 3 allocated, and 1 build in the queue that hadn't been allocated to a node yet. Moving down, this chart here shows me the trend in time over the past month of different builds. As I mouse over, I can see a little bit of information about each of those builds. The table on the side shows me the status of the build queue. So when I recorded this, there were 2 builds running. You probably can't read that, but it gives me the time that they've been running. Moving down, I have a table that shows me recent build failures. I'm happy to say that there aren't any in the last 2 months. So this table tells me a little bit about each of these builds. I can click through to view the log and see why it failed. And we built a feature to acknowledge failures so that we could track if they were something that we had actually looked at and determined it was not a problem or fixed, or if something that still needed to be reviewed. So this next view shows me all of the builds that have completed in the system. So each row in the table represents a reconstruction of one place on Mars, and gives me some information about that build, where it was centered, if it succeeded. I can enable or disable the build, which means if it looks like something broke, then I'll disable that so our users don't see it. Fortunately, that doesn't happen very often, but it's handy when it does happen. Builds can be deleted from the system. The table is searchable if I'm looking for a particular build. And we generate these preview products as part of the reconstruction process. So I can click into any of these and preview what actually was built and see how it looks without loading it into a 3D viewer. And in addition to the panorama previews, we also generate these fly-through movies that show a little bit of the 3D reconstruction. In these video preview products, it's just a camera that pans around. In the actual on-site experience, you can walk around.
What happens if you walk towards an area where you have no imagery?
We have imagery. So the question for the recording is, what happens if you walk toward an area where you have no imagery? We have imagery everywhere, but it may be orbital imagery, so it'll just get low resolution. Okay, so to store the data about source images and completed builds, we use Amazon's relational database service. So the reason we use RDS is that we get automatic snapshots. We're already running in Amazon's cloud, so automatic snapshots that can be very easily restored is a nice thing to have. It doesn't really take any maintenance. As the back end of this, we use a MySQL database. We did consider using a NoSQL solution when we were setting up the system, and decided not to because databases aren't really our problem in this application. The amount of data that we're tracking is relatively small and is pretty easily handled with a single traditional relational database. Oops. On top of our database layer, we built a REST API, as I mentioned earlier, using Loopback. So Loopback makes it easy to add the standard REST API and features on top of a data source, and it plugs into different database backends. So this gives us a little bit of database independence. If we do decide to switch out MySQL for different technology later, then the changes are isolated to just this one layer. So other parts of our system don't have to query tables in MySQL. They can just use these REST endpoints to get and post terrain builds or search with filters. And Loopback lets you add some logic and JavaScript as hooks that run when your tables are updated, so you can add business logic at that level. Another Amazon service that we use in the build manager is CloudWatch log management. So this is a way of pushing logs from your servers up into Amazon's cloud so you can see them and process them from the AWS console. So I think this is nice because if something's going on with my server, I can log into the AWS console and look at the logs instead of having to SSH in that box and then trying to remember where the log file is. And once they're in AWS, they can be filtered. They can push to Elasticsearch services if you want to do more in-depth analysis. You can set up alarms based on keywords that appear in your logs, such as errors. So this has worked out pretty well for us. It's pretty easy to set up on Linux. It's just a service that you install on your machine, some scripts from Amazon. I know that it can be done on Windows. I've not done it myself on Windows, so can't speak to that. So the next piece of the system is the build cluster. So the build cluster has a master node which is running Jenkins. Jenkins is a continuous integration system. It's similar to tools such as Bamboo and Cruise Control. And the typical use case for Jenkins is that you would have it monitor your source control repo, and when code is committed, Jenkins would pull that code, run a build, and then make the results of that build available. So it turns out compiling code is actually not that much different than reconstructing Mars terrain. You have some input images that you run some executable on, and then it produces some output that you need to put somewhere. So we use Jenkins to both compile our code for continuous integration and also to actually run the image processing jobs. So what Jenkins gives us is the ability to manage a fleet of worker nodes, configure scripts that will, or jobs or scripts that will run on those nodes, and then Jenkins handles keeping track of the build queue and parceling that work out to the nodes in the cluster. So this is the Jenkins interface. If you've used Jenkins before, I think this will look very familiar to you. Over on the side, we have a view of the build queue. So at the time I took this, there was one staging build in the queue. Down below, we have the status of the build cluster. So the master node was running a job called manage nodes, which I'll talk about in a second. We have a couple nodes offline, and then that third one is running, I think, a production build. And there's a couple more down below. This table on the right shows the job descriptions in Jenkins. So each of these is basically kind of a script that does a certain thing. So the top one is build scene staging, so that does a staging build for a certain scene. The next one is builds a production scene. There's one that builds the preview products, and a couple other miscellaneous ones. We also have Jenkins jobs configured that can create and destroy instances in EC2 and manage the fleet of worker nodes. So if I want to see information about a particular build in Jenkins, I can click through to see details on that build. I can click to see the console output either after the build is completed or while it's running if I want to see what stage in the process it's at. Jenkins tells me that this build was started 59 minutes ago and has been executing on this host, and it gives me an estimate of when the build will finish. And it gives me some information about what version of the code this was running. So this was running the production code at that certain Git hash. So Jenkins, out of the box, gives you the ability to keep track of worker nodes and parcel work out to those nodes. What it doesn't do is to dynamically create and destroy the cloud instances based on workload. So we extended Jenkins with some custom scripts to make that happen. So the way that we do this is we have a periodic task called manage nodes that runs every couple minutes on the Jenkins master, and it looks at the size of the work queue and it looks at the size of the build cluster. And if those two are too far out of whack, it will try to equalize them. So if it sees that there's more work in the cluster than there are nodes available to do it, then it will spin up a new node and then add that node to the cluster. Likewise, if it sees that the work queue is empty and there's a bunch of idle resources around, it will shut those nodes down. So the system scales within some parameters that we control to adapt to the amount of work that is actually needed at the time. So there's a little kind of Jenkins-specific trick that we use in this system. So our main job is this kind of large monolithic image processing pipeline that takes a lot of resources and runs on beefy computers. So we only want to run one instance of this task on a node at a time. So we don't want the Jenkins master to ever try to run two of these on the same node at the same time. But we do find it convenient in our Jenkins scripts to be able to call out to sub-jobs that don't take a lot of resources. So the way that we set this up so the Jenkins master will do what we want is Jenkins has this concept of execution slots on each of your nodes. So you can allocate more slots to nodes that are more powerful. So we set all of our nodes to have 7 execution slots, and then we set our main heavyweight jobs to take up 4 of them, which leaves 3 slots for lighter weight jobs that the main one will call out to. So that will make the Jenkins master never try to allocate 2 big jobs to the same node. Okay, to summarize our use of Jenkins, we have periodic tasks that run to manage the scale of the worker cluster and bring nodes online and offline depending on how much work is actually happening at the time. We use Groovy scripts to automate Jenkins, and we also call out to some command line scripts that use the Jenkins REST APIs to view the size of the build cluster and status of the system and submit jobs. And we use tags to mark different types of nodes. So we maintain separate development and production environments, and we tag some of our workers as reserved for production and others as reserved for development. So that way we know that there'll always be production nodes available when we need them. All right, so the next part of the system are the worker nodes themselves. So these are the nodes that actually run the image processing code. And these are a little bit of a different beast because these are GPU-enabled EC2 instances that run Windows 2012. So our image processing pipeline was implemented in .NET, and it runs on Windows. So when we made the move to the cloud, we just chose to keep it in that environment. So the way that we manage these is we take a stock Amazon machine image for Windows 2012, and then we install all of the dependent software that we need onto that image. So this is not actually our image processing code, but it's all the dependencies of that code. So it's the right version of .NET, and the right version of the Jenkins jars, and the right versions of the different image processing tools that we call out to, and a handful of other things. And then we bake that into our own AMI. And as our needs change, we revision that AMI and update it. We expect that to happen infrequently because it's kind of a pain to rebake it. So we try to only put things that we expect to rev fairly infrequently onto this machine image. So these are GPU-enabled instances, and in Amazon's cloud, there's two offerings in the GPU line. So they're both in the G2 family, and there's the XX large and the 8X large images. So the XX large has 1 GPU and 8 virtual CPUs, 15 gigs of RAM, and the 8X large is basically 4 of those put together. So it has 4 GPUs and 32 CPUs and 30 gigs of RAM, and is really kind of a beast of a machine. We use both of these for different things. So the life cycle of a worker is it comes online, it registers itself with the Jenkins master, and then it waits around until new work comes in. When work is available, that node will first pull our code from Git and build the version of the pipeline that it's going to run. Then it'll pull the source data that it needs from the mission data system. Then it will run the image processing pipeline, and then, assuming everything goes successfully, it will push the results to the on-site S3 bucket. And then it will notify the build manager that a new build is available. And at that point, it can go back to waiting for more work, at which point the Jenkins master will either give it another job to do, or it will shut it down if there's no work. So in setting up the system, there were a couple things that we learned. One thing that we like to do is to keep the workers basically as dumb as possible. So we create and destroy these things all the time, and we do have to install a lot of software on them, and it's a manual process to do that. So we bake as much of that as we can that we expect to not change frequently into the Amazon machine image, and then we try to keep all of the rest of our code in Git or other places that the worker can pull from. So we try to keep the workers in a state where they can be brought up very quickly and pull down the resources they need. Baking things in the AMI is necessary for us to get the workers to spin up quickly, but it's a little bit of a pain to manage. And the other thing that we found with these machines is using the GPU on the cloud. It can be a little bit troublesome. We had to fiddle around with this quite a bit to make it work. We would write code on our desktops that would work fine, and then it would not work fine on the cloud. We did get it to work, though, so it does work. So there's another thing that we use. This is another of Amazon's offerings. So EC2 has two kind of types of instances. On-demand instances are the normal ones that you pay for by the hour, and you pay a fixed rate. So there's also a spot instance market. So spot instances are a little different in that you bid what you want to pay, and then if there's excess capacity in the system and no one outbids you, then you get your instance for that price, which is great because you can get instances at much less than market value. But there's a catch, of course, and the catch is that your instance can be terminated at any time. But actually, for a lot of work, that's okay. So obviously, we don't use this for anything time-sensitive or production-critical. But for a lot of work, it's actually all right. So when we get a downlink, we need to build that new scene for the place the rover just arrived as quickly as possible. So spot instances are a bad fit for that case. But when we get new imagery for where the rover was a couple days ago, or for when we're running builds in our staging or development environments, those aren't really that time critical. And if one of the instances gets terminated, we'll just try again in a couple hours.
The spot instance is terminated, can you restart from the middle, or do you have to start from the beginning?
So the question is, if a spot instance is terminated, can you restart from the middle or from the beginning? And the answer is yes, you can restart from the middle if you program it that way. In our case, we actually choose to keep things simple and just restart from the beginning. In practice, our instances don't get shut down that often. And having said that, there were actually 2 that were killed in the last day. But other than that, they usually don't get shut down that often. But what we use this for is we bid on the 8x large instances for the price of the 2x large instances. So usually we're able to get 4 times the processing power for the same price as the small instances. So spot instances have worked out very well for us. So now I'll get into storage and distribution. This is by far the simplest part of our system. And it's really as simple as we put our builds into S3, then we use CloudFront to push those results out to data centers that are geographically closer to our end users. So we have users at partner institutions all around the country. We are at the moment restricted to North America. And then so when the on-site software on the HoloLens needs to load terrain, it's simply HTTP calls to CloudFront URLs, and those are secured with signed cookies. So I'll talk a little now about how we deploy our system. We use the Ansible tool. So this is an IT automation tool probably many people are familiar with. It's similar to tools such as Chef, Puppet, and SaltStack. And what Ansible gives us is the ability to capture the configuration of our Linux machines in code that we can check into our version control system. So the goal of this infrastructure is I would like things to be set up so that I never have to SSH into my servers. I'd like to be able to just create them and destroy them and deploy them automatically from scripts in source control and never have to SSH and manually configure things. And I would be exaggerating if I say that that's always true. Sometimes we cheat and we SSH in and manually configure things, but that's the goal. And Ansible gets us a lot closer to that goal. So Ansible organizes things into playbooks. It's a very powerful tool, and actually the session in this room later today, I think, is about deploying web apps through Ansible. So if anyone's interested in Ansible, check that out. So I'll show a couple snippets of the playbook that we use to deploy our Jenkins instance. So these are written in YAML. So the first step is we need to create a new user named Jenkins. We'll run that command as sudo. And then we need to ensure that that user has the SSH directory with the proper permissions. So we'll create a directory home/SSH, again using sudo with the proper mode. And then we need to copy some configuration files up. So we can point Ansible at the config file template and where we want to put it on the remote node and the mode we want. Ansible provides pretty good tools for templating these config files and then swapping out variables for different things. So we have a set of an environment we can deploy for production and an environment we can deploy for staging and development, and we separate these two with these variable substitutions. So when comes time to actually deploy a new one of these instances, it's as simple as creating a new EC2 instance, which we can do either through the AWS console or through an Ansible playbook. And then pointing Ansible at that instance with the -i flag and then the script to run and the environment. And then this final argument is the vault password file. So the way that Ansible deals with secret keys and credentials that need to be deployed to the remote machine is that it stores them in a file called the vault, which is encrypted and stored with your project. And when you run Ansible, you need to provide the password to unlock the vault so that it can pull out the pieces that it needs. One time when I gave this talk at JPL, almost immediately after our talk, or my talk, we accidentally terminated our build manager instance. It was complete user error on our part. So I can speak from experience that this actually really is as simple as these two commands to recreate that instance.
What's the purpose of encrypting the vault instead of just having it unencrypted?
Because if you check it into your source control system, you don't want unencrypted passwords and keys available. Also on that occasion, we learned about EC2 termination protection, which is a good thing to turn on for your critical nodes. All right, so we use Ansible to configure all of our Linux machines. We're not yet using it for Windows. I would like to be in the near future. We haven't had time to get around to setting this up. What I would like to do is, I described for our worker images, we manually configure a machine image that serves as the base of our worker node. I would like to be able to build those with Ansible instead of doing it manually, because any manual process is error prone, especially if I'm doing it. So my goal for the near future is to use Ansible to automatically provision everything we need onto an Amazon machine and then bake that into the base machine image. Okay, so to summarize a bit, things start on Mars. Curiosity rover captures new imagery. That imagery is downlinked to the mission data system on Earth. The build manager periodically pulls that system for new data. When new data is available, it's indexed into a database running MySQL on Amazon's relational database system. The build manager requests that the Jenkins master allocate a new node to do the work of running that terrain reconstruction. Jenkins will find a node to do the work, spinning up a new one if necessary. That node pulls the source files that it needs from the mission data system, runs the terrain reconstruction, and then pushes the results out to the on-site S3 bucket and notifies the build manager that a new build is available. At that point, the next, sir?
Just a couple of questions. The mission data that you download, approximately how much data is there?
That we use for a terrain build?
The data that's there, that you get back to Mars.
Oh, I'm afraid I don't know off the top of my head.
Okay. Is that data that you then put into the build manager, does that go to, I would assume, get sliced up and get passed over?
That's a good question. The way that we run the pipeline right now is we actually run it on a single node at a time. So one job runs on one node. The reason that we've done that is we chose to optimize vertically before we scale that horizontally. So for this phase of the project, our time targets were to build terrain for a scene in about the 3-hour regime, which we were able to hit by vertically optimizing and pushing some parts of the pipeline onto the GPU. So to keep things simple, we've kept things for the moment running on a single node. That said, I do not expect that to be the case going forward.
Okay, the last question, I think you just answered, it takes about 3 hours for a worker to process these?
That's correct.
Okay, thank you.
Yeah, welcome. Okay, so once the results are in the build manager and in the on-site S3 bucket, the next time our users launch the on-site software running on the HoloLens, they'll pull down the latest terrain and see the latest place on Mars next to where the rover is currently. Okay, so what I've described here is very much a snapshot of a system as we've built it now, or as we've built it and as it's running now. I'm not going to say that it's the best possible solution to this problem, and we do expect to improve this going forward. One thing we'd like to work more on is improving our auto-scaling ability. So I described how we use Jenkins to manage the size of our worker cluster and scale it up and down based on the size of the queue. Now, it may occur to you that most cloud providers offer kind of similar things that also can create distributed instances based on some kind of workload. We made the conscious decision not to use basic scaling features from a cloud provider because when we were designing the system, we wanted to maintain some level of cloud independence. So we ended up rolling some of this stuff ourselves. And it's worked out pretty well for us. But having gone through this, I think we would actually rather not be writing and maintaining that code ourselves. So we'll probably in the future be looking to see if we can swap out some of our auto-scaling logic with something that's just provided by a cloud service provider. As I mentioned before, I want to start using Ansible to manage the Windows worker AMIs more closely. That's one of the kind of the fiddly bits, manual bits of the deployment process right now that I don't like. And to your question, sir, right now the image processing pipeline is this monolithic thing that goes all the way from stereo images from the rover all the way to a 3D terrain reconstruction. Now, obviously, there's a lot that happens between these two endpoints, and we'd like to split that up into a little bit more modular services that do different things and can be scaled out more easily, because going forward, we will need to exceed the 3-hour threshold by a lot, especially looking toward 2020 when the Mars 2020 rover will land. So I do expect to do a lot more of smaller services that are scaled out horizontally, probably still using the GPU, and then we'll need to look into how to distribute the source images to the different workers that need particularly those images. Right now we're in a kind of easy parallelization world where each worker can just pull all of the stuff that it needs, and it works out fine. Okay, I'd like to acknowledge the great work of all of my colleagues on the on-site team and our partners at Microsoft. I hope you've enjoyed this talk. I hope you've learned something. If you have any questions for me during the conference, Feel free to grab me or to say hi in the hallway. If you have questions afterward, feel free to email me at parker.abercrombie@jpl.nasa.gov. If you'd like more information about the on-site project, please see our website, opslab.jpl.nasa.gov. And if you have any feedback about this talk, I would love to hear it. I'd love to hear what you liked and what you didn't like at the Google form at the bottom. With that, we have some time for questions. Sir?
You're using Windows machines for your workers.
Mm-hmm.
Why? What is are you pretty snarky about it?
Okay.
I'm not being snarky. What are the parameters that fixate you into a Windows machine? Is it because you're going to be using the Windows 3D glass hardware, or is it just because you partnered with Microsoft? You wrote specialized software on a Windows platform, which you have to completely rewrite.
Yeah. So the question is, why are we using Windows for the worker instances? To be honest, that decision was made before I joined the project, so I don't have a completely historically valid answer for you. In general, though, at the time the decision was made, they felt that was what fit the problem best. So, sir. So the question is, why can't we just throw more workers at it to reduce the 3-hour window? And yes, we can, and that's probably what we will do. We will need to rewrite parts of our pipeline to run in parallel on multiple workers. So up until now, we focused on, by design, we run on a single machine, and we focused on making it run as fast as possible on that single machine. We do parallelize extensively on cores on one machine, but we made the intentional choice not to scale out to multiple machines yet. But going forward, I think we'll do exactly what you have in mind. There's one up here, and then.
So a couple questions. One is, how does CloudFront scale, from geographic locations? And the second question is, what sort of GPU problems did you have?
Okay, so the first question was, how does CloudFront scale? I believe you meant geographically. Yeah, so I'd recommend looking at the CloudFront documentation on Amazon for its worldwide reach. Within the continental U.S., which is our region of interest, it has very adequate coverage. And the second question was, what kind of GPU problems did we run into? The challenge we ran into is that on our Windows machines, for some reason, the GPUs sometimes weren't recognized, possibly due to misconfiguration on our part, or I'm not 100% sure. I'm actually talking to some engineers at Amazon next week about exactly what was happening. And there was a question back here.
Are you looking at any existing open source Java queuing frameworks already?
Yes, we are.
What are you looking to use?
To be honest, I haven't looked into a lot of detail on this. One open source tool that caught my attention recently that I have not evaluated, so I can't really speak to, is Spinnaker, which is an open source project from Netflix. I saw an interesting presentation by some of their engineers last week, and we'll be looking more into that.
This is maybe too soon to ask this question, but are there anything that we in the open source community, like OpenCV or the Point Cloud Library or the robotics operating system, can do to improve the graphics processing situation for your application?
Yeah, okay. The question is there anything in the open source community, OpenCV and other kind of image processing libraries like that can do to improve our situation? And that's a deep question, and the short answer is yes. And my hope would actually be that some of the innovations that we've made in this pipeline can be pushed out into the open source community.
Are there any specifics, like so specifically the point cloud library can do reconstruction and those sorts of things? Are there missing features?
I don't have the details enough in my head right now to speak to that in much depth. I'd be happy to chat with you offline, though. In the back?
Did you long-term strategy for archiving?
For archiving? Our strategy at the moment is to keep things in Amazon's data system. Archival hasn't been a big focus of ours yet, but probably moving forward we'll want to sync up with other parts of the Mars mission and leverage whatever technologies they're using. I'm afraid I don't know off the top of my head how they do it.
What is the total cost of
In terms of I'm afraid I can't answer that. Sorry.
All of the scene jobs you built composed entirely of the new imagery downloaded from the Mars system, or also integrating existing imagery from previous downloads? I didn't see that in the diagram.
Oh, okay. The question is, are each of the scenes that we build comprised entirely of, I think you mean new imagery from the most recent downlink, as opposed to older imagery from earlier in the mission? And the answer is the latter. So what we will do is, for a scene, we'll find all of the images that are taken in that region of Mars. So that includes what was most recently downlinked and anything that might have been downlinked in the past. So in theory, the rover could actually drive in a circle, and you would pick up data from actually much later in the mission. This has actually happened a couple times in the mission.
So that deciding what pieces to use takes place in what part of the...
Yeah, so deciding which pieces to use, I showed a slide earlier that showed color imagery and black and white imagery next to each other, coming from different places. So this is actually a very deep question. How do you decide, if you're doing a mesh reconstruction, you have a set of images, and for any given part of that mesh, multiple images saw that place, so which one are you going to use? We have some heuristics that optimize this for our use case. There's a lot of different ways that you could do this. To give you a couple of examples, we kind of pretend that Mars is a static thing where nothing ever changes, and this is not true. This is a lie. The most obvious thing that changes is this huge Jeep-sized rover runs over it. So, and you'll even see in some of our scenes, like rover tracks appear and then disappear because, some images were captured before the rover drove and some were captured afterward. But you could imagine using your heuristics of which imagery you're going to choose to skew the reconstruction to capture the state before the rover drove or after the rover drove, depending on what you're interested in, or any number of other things.
Do you have any requirements in how to basically search the images that we're storing as 3? For example, suppose we want to tag metadata to each image so that end users are able to search and discover it. Do you have those requirements, or so what would you consider using for searching?
In this application, no, we did not have such a requirement. In other parts of the Mars Science Laboratory data system, there are images available to the public that can be searched by different things. I can't speak to exactly which technologies they're using. In this application, to finish on your point, we limited the amount of metadata that we track to really just the bare minimum of things that we need to know about. And thus far, the searching has been within the scale that we can do within a relational database. I think question over here.
Is the final data product available to the public?
The question is the final data product available to the public? The answer right now is no, but there are some thoughts in that area that unfortunately I can't share right now. But stay tuned.
Was there a particular reason why you went with Amazon instead of like a government IT outsourcer like EBS or ACS or Eris?
Not that I know of. When the decision was made, Amazon was what we chose.
Do you think that the coding build time will get to a point where you could directly stream the data coming from the rover and convert it on the fly and send it to governments?
Yes, I think that is possible. I think the more interesting question is, can you send the data from a data system directly to the HoloLens? Getting the data from Mars to Earth is actually a whole other question. And maybe not surprisingly, the bandwidth between Mars and Earth is kind of limited. Yeah, sir.
When you're processing this information, how many HoloLens users do you have? Are they like sitting waiting for this information, or do they already have like a lot on their plate that they're looking at? So do you have like wiggle room here, or are they constantly calling you and saying?
So the question is basically how soon do our users want the data, I think, to paraphrase. And the answer is now. It's actually a very subtle question that you're asking. So the way that Mars planning works is there are certain planning meetings that are time sensitive for planning rover operations. The way that those meetings line up with how data comes down from Mars is very complicated. Ideally, our terrain would always be ready at the beginning of the meetings. That's not always the case. So in some cases, we may get down like in the middle of the night and have the rest of the night to do the work, in which case, no one is calling us. And in some cases, we might get down like half an hour before it's supposed to be ready, in which case it won't be ready. So the answer is the users would like the data as fast as possible, and we're trying to meet that need. Skylar.
Is there any way to view the data without needing HoloLens? Like if they're in a big meeting, can they put it up on a screen or something?
The question is there a way to view the data without using the HoloLens? In On-Site today, no, it is a HoloLens-only application. However, I don't expect that to stay that way forever. In fact, not for long. Sir?
How does the data look when you're looking at it through HoloLens? Is it like Star Trek's holodeck? Or like
That's what we aim to make it.
there is something better at looking at it through HoloLens versus looking at it as an image cooler, or actually get benefit?
Okay, that's a great question, and that really speaks to why did we even do this, right? Because we have these 2D images already, so why even bother with this 3D reconstruction? And yes, the reason that we do this is that I think there is something perceptually different in looking at images in 3D and versus 2D. Like ideally, you would actually send a scientist to Mars and they would look at rocks for real. We can't do that. So the next best thing is we can put a scientist in virtual reality. And using the HoloLens, you're not tied to a different, certain place. You're tracked, so you can move around the scene and walk around as if you were there. Clearly, it's not quite as good as being there, but you can use some of the spatial cues that you use in your everyday, life on Earth to understand the scene around you. And at the end of the day, geologists are looking at rocks. They're trying to understand how big are the rocks, how are the rocks, laid out in relation to the scene around them. And it's very hard to do this in a 2D image. And there was some work before this project started that motivated the whole thing that tried to quantify how people understand a scene that they see in a panorama image versus a scene that they see in virtual reality. And I'm not going to go into that today because I don't have the numbers in front of me. But the punchline is that people are actually dramatically more accurate in understanding a scene when they see it immersively than when they look at it in 2D. Even experts who do this in 2D. So that's the whole motivation for building this application that lets you look at Mars immersively. Skylar.
When viewing the data with the HoloLens, if you continue along in the thing and you get to the edge where the quality is lower, would there be any way of notifying the user there's this better quality data that you can view, or how does that switching work?
So the question is, I think you're asking if you walked from one scene to another along the rover's path, would you switch from orbital into the new scene? That's something that we would like to support at some point, and unfortunately we don't today.
Why did you choose Mars as opposed to any other planet?
Well, conveniently we have a rover on Mars. So the question is, why did we choose Mars as opposed to other planets? And sorry to be a little bit snarky there. We have much better data on the surface of Mars than we have for other planets. If you think back to the orbital maps that I showed at the beginning of my talk, there's a lot that you can see from orbit. And honestly, Mars is absolutely beautiful when seen from orbit, as are other planets and moons. But for a virtual reality experience where you're trying to put someone on the surface, orbital data just doesn't really get you there. It's just not high enough resolution. So where we have really good surface data is Mars, where we have robots that collect this for us. At the moment, we don't have such data for other places. Earth, yeah, okay, Earth is a counterexample. I'm not sure who was first. Ma'am.
I know Mars mission takes decades to plan. So actually went in the pipeline and someone said, it'd be cool, we'll make a VR out of all this data and get
Okay, the question is, when in the process of planning the Mars mission did this idea of creating a virtual reality tool come up? I'm not entirely sure, to be honest. I've been at JPL for a year and a half, so I was not at JPL when the Curiosity landed. I know that the ideas of looking at Mars in virtual reality have been around for years and years. This particular project has been going on for about 2 years, and this group has been doing work in this area for much longer than that. But when the germ of the idea that is now on-site was born, I'm afraid I don't know. Okay, the question is there one for the moon? We are not doing one for the moon today. I don't know if we will or not. I think you were first, sir.
It was my understanding that HoloLens is more of an augmented reality versus an Oculus, which actually is fully immersive. Is there a reason why you went with HoloLens? The environment in which the users are experiencing this, maybe speech was about
Sure. So the question is there a reason that we chose an augmented reality technology such as the HoloLens versus a virtual reality technology such as Oculus? One thing that we get from augmented reality is that we wanted our users to be able to continue using the tools they're used to while they're in their virtual world. So I didn't really go into how on-site works in user interface, but we actually detect where your computer screen is, and then we cut that out from Mars. So you see Mars everywhere else, and then you see your computer screen. So the reason we do that is you can continue using the tools that you usually use to work on data from Mars while you're looking at Mars in virtual reality.
How accurate are the spatial details maintained when you're converting to a 3D environment, just like angles and distance?
Sure. Yes, so the question is, how accurately are the spatial details maintained when going from 2D to a 3D reconstruction? This is a deep question, so I'm not going to get too deep into it. We aim for the kind of centimeter-ish level accuracy in our mesh. There's a lot of ways that noise can come into the system, and in fact, the source images that we use, we get range products out of those, and just by the nature of how stereo correlation works, the quality of that range falls off as you get further from the rover. Fortunately, usually the things we're interested in are near the rover, so that's not too much of a problem for us. One of our next steps actually is going to be doing some more quantitative analysis of our mesh versus the input images.
Is it possible or how tied is this to Curiosity, and is it possible to post-process data from previous missions?
So the question is, how specific is this technology to Curiosity, and is it possible to process data from other missions? I assume you were talking about perhaps Spirit or Opportunity or other Mars rovers. In general, this is not specific to Curiosity. This is something that can be applied to any kind of stereo reconstruction process. In practice, currently we are a little overfit to Curiosity. We have talked about supporting other Mars missions. Right now, we don't have any plans to do so because it will take a bit of development effort to make it happen. Skylar.
Does this use location data from where the rover is and which way the camera's pointing to help it stitch the images together, or does it just look at the images themselves?
The question is, do we use location data about where the rover is to inform the image stitching process? And the answer is yes, we do. I think that's a little more detail than I want to get into today. I'd be happy to chat with you offline. Okay, maybe one more question.
Can you convince them to show this at the next JPL?
Well, we'll see. Okay, well, thank you all very much.